In the world of programming, memory safety is crucial. Errors like buffer overflows and data races can lead to unpredictable behavior and security vulnerabilities. Rust offers a unique solution by implementing ownership rules, which prevent these common memory bugs. This ensures your applications are both robust and secure, giving you confidence in your code's reliability. Continuing from why memory safety matters, let's delve into the issues prevalent in many programming languages. A null pointer dereference happens when your program tries to use a pointer that hasn't been set to a valid memory location. It's like following an address that leads nowhere. Data races occur when two threads access shared data simultaneously, and at least one of the accesses is a write. This can lead to unpredictable behavior and bugs. Use-after-free errors arise when a program continues to use memory that has already been deallocated, potentially corrupting other parts of the program. These are challenges Rust aims to eliminate with its innovative ownership model. So, how does Rust tackle these memory issues we've just mentioned? The secret lies in its ownership model. At its core, Rust ensures memory safety without needing a garbage collector by enforcing strict rules around ownership, borrowing, and lifetimes. Every piece of data in Rust has a single owner, ensuring that when the owner goes out of scope, the data is deallocated, preventing use-after-free errors. Borrowing allows for multiple references to data, but with rules that prevent data races. Lifetimes are Rust's way of tracking how long references are valid, ensuring that references never outlive the data they point to. Now, let's see Rust's ownership model in action with a simple code example. Here, we have a string, and we're demonstrating how Rust prevents conflicting modifications through its borrowing rules. We first create two immutable references, P1 and P2, to the string. Rust allows multiple immutable borrows, avoiding data races. However, if we try to modify the string with push_str at this point, Rust will throw a compile time error, as mutable and immutable borrows cannot coexist. This ensures our program remains safe and free from memory issues. As we saw in the previous example, Rust's ownership model is powerful, but it can be tricky to master. One common pitfall is misunderstanding lifetimes, which can lead to unresolved borrow issues. Always ensure your references are correctly scoped and never outlive the data they point to. Another best practice is to avoid unnecessary cloning, which can impact performance. Instead, utilize borrowing effectively to keep your code clean and efficient. Understanding these nuances will make you a more proficient Rust developer. Now that we've explored Rust's ownership model and memory safety features, you should have a clearer understanding of how these concepts guard against common programming pitfalls. Remember, lifetimes help manage borrow scopes, and borrowing avoids unnecessary data copying. These tools are the foundation of writing efficient, safe Rust code. Continue practicing, and you'll become more adept at leveraging Rust's strengths. We'd love to hear about your experiences with Rust. What challenges have you faced, and how have you overcome them? Share your thoughts or questions in the comments below.